Plinio. So let me get my, so first off, experts, if you haven't uploaded your poster assessments, please do. Late last night, we posted a sort of rough schedule for the field trip. We will be talking about that schedule and more details about the field trip at the end of the day today. So I think a lot of you will be able to ask a lot of your questions then. And we also plan to put a bit more information in the info packet as well. The workroom is going to be in A5 again, so that's where it was on the first day, and that's also where the time series analysis workshop is going to be. So that's just one floor below us, sort of like on the other side of the building. And then finally, after the first lecture today, there's going to be a lab tour, which I believe is not in this building and is maybe like a 10-minute walk away. Is that right, Plinio? And what we're going to do is divide the group in half. So half will go first, and then the second half will go later. And we are going to have an hour-and-a-half long coffee break. And we'll divide you into groups, I think, after the lecture. So the coffee break will go from what, like about 9:30 to 11. Okay. So I think, is that it for announcements? Okay. Great. So then I think we can get to our first talk of the day. So our first speaker is Plinio Jaqueto. He is a postdoctoral researcher at the Institute of Rock Magnetism at the University of Minnesota. He has his PhD in geophysics from Sao Paulo, and he has experience in geosciences with emphasis on rock magnetism, karst systems, and Speleothem records. Today he will give a talk on paleomagnetism and Speleothem. So take it away.
Thank you very much for this invitation. I've been raised and born in this university for a long time, for like 10 years, and then it's not in this institute, it's the institute that we're going to visit. I'm a geophysicist, and I came here a lot to talk to all this research group in Speleothems, and that's where I'm learning a lot of my research. So I'll be talking a little bit about the research that is being conducting in this subject, which should be like it's not a too outsider. I'm not an outsider of this research, I hope, for everyone. So this is the outline of my talk today. So we know northern lights a lot. So it's an effect of the Earth's magnetic field, and especially if you go to high latitudes, you see this effect of interaction of the Earth's magnetic field with solar winds. And I'm going to talk a little bit like how the record of rock magnetism can be used to retrieve information about the Earth's magnetic field. So first, we know that the Earth's magnetic field is very important to our life, so it protects us from this solar wind. And this is supposed to be happening since like 4 billion years ago. So there is a lot of discussion of when it started, and it provides us an atmosphere, and it's very important to understand its evolution through time. So to describe the Earth's magnetic field, it's a vector, so it has intensity, then there is a direction. So if you take a compass, you know where the magnetic north is, you know the inclination, and this is the most simple description. And a simple description that we can use is like a dipolar field. We know that the Earth's magnetic field makes a 10 degrees from the geographic, and it changes through time. And mainly the magnetic field is generated from in the outer core, so there is like a liquid outer core that with convection generates the Earth's magnetic field, and it's the most simple description. But when we look at the field today, we see a lot of features. One of these features that we should look this, I'm pretty sure that Matthias is gonna show maps that do not look like this, but it's gonna be a lot of colorful too. So we know that the intensity of the Earth is very high during high latitudes, and it's the minimum around the equator. But then in 2020, if you look, there is a feature that we call the South Atlantic anomaly. It's the lowest intensity of the Earth, and it causes some problems sometimes. So this is a video that is not gonna work, so I made a backup. Yeah, so what happens here is this is called like a single upset event, which actually from swarm satellites, there is, every time there is a failure, you see these black dots here. So we can see there is a very strong correlation between like the lowest intensity point of the Earth with the failure of satellites. But to say something that everyone asked me, we are safe. So they took some flights from Buenos Aires to Paris to know if it's safe for humans, and it is safe for humans. We don't fly too high to get this effect in the way that it's impacts us. But we don't know a lot about this feature, like when it started and when it's going. So to understand that, we want to know the origins of the Earth's magnetic field and how it evolves with time. So we can describe the Earth's magnetic field through spherical harmonical functions. I know this is it's a very big equation, but there is something important. This started with Gauss. So Carl Friedrich Gauss did the first description of the Earth, and we can, with this, what happens is that we can collect data all over the world, and we can calculate the Gauss coefficients. So with this, we can have a sense of the power spectra of the Earth's magnetic field, and try to disentangle the origins of this. So using this type of description, we can do a downward continuation to the core mantle boundary, so where the Earth's magnetic field is mainly generated. So we consider this, in this approach, that the mantle does not have any magnetic field being generated. So like using the Gauss coefficients, the most simple one is the dipolar field, which accounts for more than 90% of the intensity of the Earth. But then we start to add the higher frequency. So this is a quadrupolar, this is an octopolar, and then you name it until you go to the degree 13 or 16, depends of your description. So when we look at the core mantle boundary, we start to see some high frequency changes. So we suppose here to have like everything should be blue here and everything should be red here. But then when we look at the core mantle boundary, we see that there is these regions here that are on the opposite side. So these regions are called like the reversed flux patches, and they are thought to be responsible for the South Atlantic anomaly. So this makes the Earth's magnetic field a little bit lower than expected for the region. So when we look at the surface, we see that this is, at the surface we don't have this very high frequency. So what are the challenges? What is the evolution of the Earth's magnetic field for the past? So when we look for the Holocene and I'm always struggling with paleomagnetism because I always want them to use before present in their scale, but they refuse to use before present, so I think it's a unique feature for our community. But we see here is the present, and here we see the strong decay, and then we see that there was a strong variation. But how can we retrieve this information? So we use mainly sediments, and we see the volcanic, and also volcanic and archaeomagnetic. So, and also some past navigation features. So what we see is that using this type of data from the past, we can reconstruct this using the spherical harmonical functions. We can describe the Earth's magnetic field, and then we can try to understand its evolution. But when we look here, I think this is also true for our paleoclimate community, it's not equal. So we see like South America contributes to less than 5% of the data, and that's where we don't know like what's the evolution of the South Atlantic anomaly and what is the impact of us. So one of the problems when trying to model this is the regularization parameters. So field data in one plot like this in South America, if you look for South America curve, it always looks like this data. So we don't think that that's a good sign of description of the evolution of the Earth. So this is I took some model, very recent model, and tried to understand like how does it change. So here we can describe how this vector is changing through time. So this is the year 1900. So when we look for the 1950, we see there is like an expansion of this feature, and inclination is also changing. So look here. So, and then year 2000 and year 2020. So we see there is actually there is an expansion of the South Atlantic anomaly, and then we see that there is a new feature that's growing under South Africa, which has been interpreted as there is two mechanisms. One of them is the control of the core mantle. So the convection of the core, the outer core makes it some reversed flux patches, and some others claim that there is like a top-down control, which is like some temperature gradient will cause this reversed flux boundaries to start the growing of new lines. So that's why I'm here. So using Speleothem can be useful. So we can use, if iron oxides are present in this type of material and they can be dated, we would love to use this as to understand the evolution, as a terrestrial record for the Earth's magnetic field evolution. So Max Hansen did a talk here, and then he showed like a few seconds you're able to lock the calcite precipitation. And then when you grow your calcite, there are some very few amounts of magnetic minerals that they are able to align with the Earth's magnetic field at the time of their forming, and this is locked for time. So if we have the perfect balance between having a good age control and a good amount of iron oxides, we can retrieve this information of the Earth's magnetic field. So we are actually retrieving information that is happening in the core mantle boundary into our cave. So that's very unique. And I got a lot of this talking to Ivo, which was Ivo and Chico and Nicolas and a lot of this research group at CIS. We have been discussing this a lot. So, but it's not very, one of the main challenges that we have to face is that's very weak, the magnetization, and also the efficiency of the magnetization in sediments. They are not very well constrained, so we don't have a physical understanding of the alignment of the grains. How much are necessary to align? We think from simulations like if you have at least 5% of your iron oxides are able to align with the Earth's magnetic field, you are able to retrieve the information of it. So ideally, we would be able to retrieve annual to millennial resolution, and this would be much better than we have from lake sediments. So what makes it possible? I'm pretty sure a lot of you have already seen this picture. So this is a hysteresis. It started in rock magnetism, but now we see a lot of this in financial. They start to use this because there is some hysteresis after there is something happening in the financial. But the main message here is that when we here in the x-axis, so stop me if you don't understand any graph. You can stop me a lot, don't worry. So here I have, this is like applied field, which is the B, and then this is magnetization in the y-axis. So what makes it possible to understand the remanence of the minerals? So we apply strong field, and so we are aligning all the magnetic grains here. And then when we go back and we apply in the other directions, and then we reach this point here, which is 0. So there is no applied field in the sample, and it still holds some remanence signal. So this is mainly what makes paleomagnetism possible. So there are some important features, and we're going to talk this a little bit later. Why it stays there? So there is a concept from physics, which is a relaxation time. So there is a fight between magnetic energy and thermal energy. So if the anisotropy of your grain is big enough to surpass the thermal energy, you have a relaxation time that goes to billions of years. So grains like 20 to 30 nanometers are capable of retaining information about the Earth's magnetic field for the age of the solar system. So, but yeah, it's not new. Speleothem magnetism, it started in 1979. I think Hubert showed that after him, I think 82, he did a lot of work in dirty calcites. I think there is a reason for this. He was trying to date a lot of samples. And then, yeah, the results were very promising, but the error in the ages were too big. So then there was not many work later. So I like to use this image from the book from Fairchild and Baker. So Speleothem magnetism started in 1979, and then there were very, very few records up to 2010. And then we can see that we lost all this gap of evolution of Speleothem science. And now, since 2010, there were like many more advances in also in the rock magnetism, which you will see in the lab tour. So superconducting magnetometers, and also evolution in the dating processes, and this makes it more easily or able to use. So I did some compilation of only using Speleothems. So we see that there is like after 2010 there is 26 studies, which will be like a week in Speleothem science. Here is like 13 years. So there is a lot to do, and there are very few people, and this kind of holds back because more people doing, we evolve faster, and I think that's a good point to start now. So there are works going on all over the time, and I'm gonna show some of them. So first, how can we study? So one big discussion is that the recurrency of the South Atlantic anomaly. We only started dating using geomagnetic observatories in the 1900s, 19th century. And then we were trying to think like, can we go back in time, how it evolves? Can we have a high resolution record of this? So we take this sample. I know it's not the whitish samples that we see a lot in these presentations. So, but it works a lot for my research itself. So what I do using here, I try to take the powder from the more cleanest layers that I can, and then with this we can have some reasonable age model, and then we try to recover the vector. What is the Earth's magnetic field vector that's recorded in these samples? So we can have a declination record, the inclination, and the intensity in some cases. So here, this is two studies. So the first one we saw, this is the white dots here with the white line, with the red line, sorry. And then we see that there is a strong variations in the Earth's magnetic field in the sample. And this thick line here, they are models. And then there's a lot of things that we can start to understand. One is that models, because there is no many data in South America, they tend to be very smooth sometimes, and sometimes they have been, because they are using the Argentinian record, they can fluctuate a lot. So it's pretty hard to understand if you don't have that's why parameterization is a challenge. So there is a lot of techniques that they're trying to develop on this subject, but we see the strong variations of the Earth's magnetic field recorded in South America, and then during Holocene, these changes were not so strong. So from the first study, we concluded, actually we see that there is a lag in variations in South Africa and in South America. So this was not actually thought to happen at that time, but showed that there is some kind of recurrency of this feature. And then from the past, we're going to see now like we can take the angular variation. So we're seeing like how much this vector is changing through time. So if we have a very strong changes in this vector, what it means that we are seeing a lot of activity of the Earth's magnetic field. If we don't see a lot of change, so maybe we're not seeing these expressions of these non-dipolar features. So what we see here is that there is this South Atlantic anomaly going a lot for the last 2,000 years. And then when we look for the middle Holocene, we don't see this. So even models sometimes can be overinterpreted these records. Also, one key feature that we have very few records in general records, like lake sediments or volcanic, is the Lachamp, which was the time that the Earth's magnetic field went to, it was in the North Pole, and then it went to -45 in latitude, and then it went back. So, and this was using a stalagmite from US, they were able to capture like this big swing in the inclination. So it was like around 50, and then it went to 0 degree, and then it went back. So it recovered this. And using a Speleothem, they were able to constrain the main phase of these changes. And yeah, so it was only possible with all these new records. And now I'm going to change outlines. Any questions about these graphs? All right, so another application that we have, and we're trying to show, is environmental magnetism. So what iron is a very rich and abundant, like the fourth most common element of the crust. So if we understand the composition of the iron oxides and concentration, they should mean something that is going to change in the atmosphere. So in the atmosphere, in the Earth systems. So we can do a very nice characterization of all this, and why and how. So how can we do this? So during the lab tour, we're going to see like a lot of equipment that we can try to understand this. What is the message? Is that like calcite, it's a diamagnetic minerals. So all minerals have magnetic properties. So diamagnetic is the most basic, and we see that diamagnetic materials, they do not contain unpaired electrons. So the more magnetic moments of them cancel each other, and then they are very weak. So they are present, but they are very weak. So we apply a field here, and we have like a response in the opposite direction. So if you want to know your calcite, just ask for a Plinio magnetism. It's going to measure it, and then you can table this calcite. Another one is the paramagnetism. So these electrons, they have a non-zero magnetic moment, especially clays. So, but what happens that we apply a field here in the x-axis, and then we have a magnetization in the y-axis, and then when we remove the field, it goes to 0. So it aligns, and then it returns to 0. So clays, usually they have this paramagnetic signal. But then what is the main phase? And why do we have a lab? I think Carolina is going to talk a lot about this, but the properties of keeping the remnants present, it's very important to us. So there is actually 3 different types of ferromagnetism. Actually, there is 4 of them. One is mainly like pure iron. But when we talk about like ferromagnetism, what we are seeing is that the adjacent atomic moments, they interact very strongly. So if you think like there is like we apply a field here, and then there is this response of going to all anti-parallel, but they're not in equilibrium. So there is like there is a remnants pointing to one direction. So an example of ferromagnetic mineral are magnetite, and then I want you to take a look at this. So saturation magnetization, so it goes to 92 ampere meters squared by kilogram. And then we see a lot of this. But then we can also look at canted antiferromagnetism. So especially hematite, we have this, they are like opposite direction, but they have a slightly difference. So there is like a 2.3 degrees between each grain. And then this arises a ferromagnetism. So it stays the remnants. But look at this, it's like half ampere meter square by kilogram. And then also a very common mineral in caves are goethite. And then what happens is that you have a defect. Usually I always, when I go to talks, I see like people usually they sit in the same spot during the whole week. And then when someone changes location, you have this defect. So that's what's arising the magnetism of goethite. Goethite is also, it's even smaller magnetization. And how do we track this? So if you go to radiomagnetism lab, they do a lot of low temperature magnetometry. So there is important phase transitions that happen and help us to identify what's going on. So here in the black line, this is temperature in the x-axis, remanence in the y-axis, and then we start at 300 at Kelvin, and then we see this big shift around 120 Kelvin. What's happened is that the magnetite, it has the cubic crystal changes to monoclinic, and this changes all the magnetic properties, not only magnetic, but also caloric and other properties. And then there is a remanence that recovers it back. So there is always a memory when we talk about remanence magnetic minerals. Also, hematite, there is the Morin transition around 250. So remember when I told you that there is like this 2.3 degrees. When it crosses this, it cancels each other, and then we lose all the remnants. And goethite, which is very challenging to track, but we see this, it increases as we go to low temperature. There is some contamination with magnetite, but that's a way to track these minerals through time. Also, we are able to measure this part here, which is the BC. BC is the coercivity force. It's a property of the anisotropy of the grain, and it changes for grain sizes. So this is like the curve for magnetite. We see that we can actually measure like 5 nanometers, 10 nanometers with just a hysteresis loop, and then we can track like how the coercivity changes through grain diameter. So that's an important feature that we can track what's going on in the car system. So, but how environmental magnetism got its foundation? So through ice rafted debris, there is a lot of research that happened in the past with using magnetic susceptibility. So there is like peaks in magnetic susceptibility related to the Heinrich events. So the bigger grain sizes, we see these peaks, they are aligned with the Heinrich event. So the iceberg and the melting brought all these continental grains, and they have been using these properties. So if you look for colors of the hematite, goethite, and magnetite, it's very diagnostic, especially if you're looking for speleothems, and I came here a lot to look for speleothems that are ideal for my research. Usually what I look just as a starting point are colors. So hematite, goethite, and magnetite, they have all these colors, although fulvic acids also have colors that are not related to the iron oxide, so there is always a lot of testing to understand this signal that is processed. So this is a graph that they follow, like how can we use speleothem magnetism to track climate changes. So anthropogenic impacts of soils. So how does farm use in the car system, and how this would change the delivery of these iron oxides. So a lactose material through especially flooding events that will bring iron oxides from all the catchment area, and this will be later transported. And also deposition through the drip waters. And then if you look for very fine scale, we can see that we expect to have the tritomagnetic particles from flood water. And also what we see a lot actually is a lot of goethite, which we measurements in TEM see a lot of the in situ growing of goethite. And this has been a very good challenge to understand like what it's meaning in terms of climate. But we also see these magnetic particles that are deposited from drip waters. They are very low concentration, and that's when we are thinking about like blocking the magnetization and recovering, so there is enough time to align some of these grains. So thinking now about karst, there is this feature, it's called magnetic enhancement in soils. So in the A horizon, there is a very strong enrichment. And this is a subject that is being studied by a lot of researchers, and it's not a clear origin. We think there is some activity, microbial activity, and also it can be like paleofires and a lot of others, like dust that would cause this. So one of the candidates that started in the 70s to be studied are like bacteria with intracellular origin. And what is mainly see is like, look at this, it's very organized and it's inside the bacteria. And also we can have some extracellular origin. So they're not very organized. We see that the grain size are much smaller, and mainly they are in the what we call like super paramagnetic size, which is not ideal for remnants records. But we think that this could be the strongest signal from magnetizing soils. So I think this is fascinating for me. Like 10 grams of cells could produce over a kilogram of magnetite during their lifespan. So what is fun is this could be like the main source of the magnetic enhancement. And what it means for, if you're thinking about like the karst system and when it's going to be deposited. But it's not the only organic. We can also think about like inorganic origin of these magnetic minerals. So ferrihydrite is it'll be like the precursor of these changes. And then we can go through an intermediate phase with hematite, and this could go like to rapid oxidation for goethite, and then it will be reduced. It could be reduced to magnetite that will be readily. We have like this we call surface oxidation. So we have a core of magnetite, and then especially through diffusion of oxygen, you have a core shell structure that we call, and then you have like magnemite around and magnetite core. And we try to track this through a lot of low temperature curves. There is some features that we see of this transformation. So now I'm going to talk a little bit about some results that they tried to untangle. I saw that Hubert showed this sample. I think that we can do like a whole summer school or just about this sample. I think there is like more than 20 works on only using this sample. So it's very fascinating to me. And Caitlin also showed results of this. So when they did like rock magnetism in this sample, what they saw is that this is Holocene. So they see some high concentration of magnetic minerals during dry periods, and very low concentration during wet periods they see a strong concentration of magnetic minerals, and during dry periods they don't see this. So there is like how it's being delivered in the cave. And yeah, that's they try to understand like the flux, like how much magnetic minerals are being flushed into the stalagmites. Also, what I do is that because there are so many records of this sample, I take the magnetic minerals and I start to compare like with all new papers that comes from this sample. So it's fascinating how big can we go. So like taking the fatty acids, the work from Wang in 2019, it was able to see like C3 and C4, and then I compare with the iron oxides, the concentration of magnetic signal. although it's not a perfect correlation, and I did not even try, I just want to show and provoke that we can do more rock magnetism and try to understand what's going on there. So we see that there is some kind of correlation, and although carbon-13 and Baldir talk about all of this, like changes and how hard it is to interpret carbon isotopes, but we see that there is some correlation, and this could be related to the bacteria, to extracellular bacteria, we don't know, vegetation changes. So I think there is a lot of, we need to study even more and try to combine this. So this is like, I tried to make a database because when I was starting, someone was always pushing me, you need to do a database. Every time you need to do a database, otherwise it's hard to understand the big picture of what's going on. And for me, I came here and I took like 4 cores of the sides of the stalagmites, and I was expecting to see a lot of differences. Also, this should be related to some biomes and changes in the cut. So I took like, these are the green circles, that's the ones that I use, and then I came with this very, very weird diagram. So, but I'm going to show it in a different way. So what I do is that I do some log Gaussian fit. So I took some soil samples, which are the dashed green line, and then the carbonate, when it was possible to collect the carbonate, and then the stalagmite. So we see that there is a very strong resemblance between the soil and the stalagmite. And also we compare to the literature for like pedogenic extracellular magnetite, pedogenic origin, and detrital. And then when we look here at this diagram, now it should be easier, we are seeing like a coercivity of the magnetic minerals as a function of the grain size. It clusters the soil and the stalagmite, showing some kind of the same origin all over the Brazil at least. And then carbonates, they have a little bit higher coercivity. So one of the questions that I got from my community is that, am I just seeing like the weathering of the carbonate being deposited and bringing all these magnetic minerals? So I don't see this very clear relationship. So this is pointing that we have an active epikarst at least. This is not constrained by age, so just bear in mind that this was like the first try to do a database and try to understand the big picture of what's going on. So what the future brings to us. So there is a lot of magnetic microscopy. I know you all saw Samuel present poster yesterday, and he's been developing and pushing a lot of these techniques over time. And this one was trying to understand the flooding in a cave. So what they do, they did a map of the magnetic. So yeah, there is a very strong similarity between the magnetic minerals and the dirty layers. And how to interpret this? This is a US sample from Minnesota, and what they see is that the full relief half maximum, it changes when we start from 1900s. So we see like if you think about the Gaussian distribution, it'll be like a bigger dispersion of your fitting, of your Gaussian fit. So, and they try to interpret this, or actually they interpret this as a change in the farm use. So there is a lot of farming going on in Minnesota at the time. So farm development would increase the amount of magnetic minerals that's being deposited through flood layers in these caves. Also QDM, which is semi-specialist, they use a sample from Brazil, the one that we also got the South Atlantic anomaly record, and try to understand at a very high resolution. So the challenges are there. If you should talk to Sammy more about this, but he'll be happy to talk more about this, how to get these maps. So there is a map of the magnetic minerals, and it's very high resolution. At first we thought, oh, can we get to the same resolution as isotopes? But I think we can get like a 200 micron map.
The pixel size on our maps are like 1 micron.
1 micron. So there is a resolution of 1 micron that you can have these types of images. So you can imagine that we are a little bit beyond the isotopes. So maybe we need to go back and compare it. So very hard to compare. So you can see here the variations. And first using the same sample, but actually pieces of this sample, we start to see some features at centennial scale. So there is like medieval climate anomaly and magnetic minerals. So we can easily interpret this as just concentration of magnetic minerals. Yeah, the resolution is not even close to great, but it gives us some ideas. So during the medieval climate anomaly, we combined with carbon isotopes to interpret this. So changes in vegetation are associated with a little bit higher magnetization values. So and this was the opposite of what everyone was thinking. But the other works, they were thinking about millennial scale. Here we're just looking for a very constrained period. So how we interpret this, and then during the more wet period, there is also like less magnetic minerals and changes in vegetation. So combining this, we came with the idea that actually what we are seeing is that during dry phases, you are able to mobilize more of the soil, and this will be delivered more into the drip water, and that's when we combining carbon isotopes and magnetism seems to be a successful way to understand this. So I would like to bring some challenges that I think there's a lot to develop. There is a lot of basic research. There is a lot of like high-end environmental research to be done. Magnetite and magnemite are the main minerals that we see. We think that they are incorporated through drip water and flooding events. There are very few cave monitoring that are targeting magnetic minerals. And this should be, we know, and we're always discussing like, how can we do this in more systematic, in a way that we have a more understanding of the processes. Also, nanohematite is present, and we did not interpret a lot of this, so there's a lot of challenges of understanding how hematite is there and what is the climatic meaning of this. Goethite is formed probably also in soils and also in situ, so changes in the pH would actually favor the formation of goethite. Cave ventilation is also something that it brings some magnetic minerals, but we don't have monitoring. I know that Sam is doing this, and this is a good thing. So we have all the questions that you did like between this interval of like 1998 to 2010, we kind of missed, and then we try to recover this information. So soil forming and transport for drip waters. So what it means for us, for water, you interpret this as a recharge in the epikarst and then it's delivered. For magnetism, we have to take some assumptions. So as soil is being formed, when it's delivered, is it the same time? How long it takes for the soil to be formed and to be stable, and then when it's delivered there? So it's a question that is like it's an open system, and then we think there is always soil and then it's being delivered, or no, there is other changes. So because I have some few minutes, I would like to talk also some applications that they do. So cave sediments have been used. So there are a lot of digging. You saw me in Valdir's presentation that I was digging some holes in here. So this is not my study, but what they found is that there is actually a strong intensity of the Earth's magnetic field around 3000, and it's being interpreted as a geomagnetic field spike, and this would mean like a strong changes in the core mantle boundary. Also some results, especially in Slovenia, they have been doing like very great work of magnetostratigraphy, so you can try to understand the cave infilling through the crown. So because there's magnetic field, it reverses all over, so it's a global feature. You can try to understand when there is a lot of cave infilling through the polarity that's recorded in these grains. So yeah, a lot of people showed these elements. So there is a chapter talking about the magnetism of Speleothems. So if you like to read and understand, no, that's it. So yeah, because people is made by science, I have been working with like very great researchers all over the time, during my life, and look for Carolina and Samuel. They have been doing a lot of good research here. So thank you.
Thank you, Plinio, for a great talk. Do you have any questions? Yeah.
At the risk that it's a stupid question, let's try this, right?
Yeah.
I find this super interesting, the entire thing. I cannot completely oversee it. A very practical question, right? If I would now take one of my stalagmites and hand it to you, what are the chances that you get enough signal for example, reconstructing the Earth magnetic field or even these environmental things?
That's a good question. I can show you through the database. So mainly I would look for clay minerals. If you have clay minerals like this one provide good results, this one too, all this one, so you should have some amount of clay minerals there. And they probably will retrieve you good amount of magnetic minerals. Because we detect something like parts per trillion. Because remember when we talk about like magnetite? So you can think that we detect, let me just, I know it's not. So we detect 10 to the minus 15 ampere meter squared. So very small amount.
So then most stalagmites, if you have a layer where let's say more clay rich, that's where the chances are.
Yeah. Yes. And then, yeah, that's it.
Thank you.
Yeah, my challenge is, I would like to know like how Juan would think, because every time I go to the lab to do some dating, people look at me, no, don't measure this sample here.
Yeah, but you have these alternations, right? So you can have relatively clean and relatively dirty, and then so you can do your stuff, and the people are relatively happy still, I guess.
Yeah, and for like, because there is not many records, if I have like an error of like 400 years in like 10,000 year sample, it's okay, because when you compare to lake sediments for rock magnetism, this is amazing for 100 years. So I'm not very like, I don't want to do like yearly resolution all the time. It'll be great, but it's okay.
Yeah, go ahead.
In the previous slides, the database. So in all the images, I've seen is like we have taken sampling from the edges of the stalagmite. So why is it the edges, not the axis?
That's because I was doing the database. So when we're doing the vector, we took the central part of the stalagmite. But because I was just investigating the amount of magnetic minerals, I took the sides. And actually, I'm doing some research where I'm seeing there is an effect of the sides. So the deposition is like you're doing the deposition with some deep, and this has some effect of the gravity and where the mineral fits. There is something that we also do, I think Carolina is being developed this, is magnetic anisotropy. So because we think that calcite grows like 90 degrees, and we can also try to understand like how the magnetic minerals have, how their anisotropy fits to the calcite. And it's very basic research for like a lot of physics, but it's also another possibility of understanding the evolution.
Suppose if I have a illuminate magnetite and aberrate in my sample, so how many grains are there for magnetic?
Sorry?
If I have a magnetic grains in my sample, so how many grains are required for the magnetic?
How many grains? He asked like how many grains I have in a stalagmite. Probably billions of grains. Because they are very tiny. So because they are like nanometers, they're like, mainly when I talk like, they're like in the super paramagnetic range, so they have like 5 nanometers, 1 nanometers. We're mainly looking for like something that's a little bit bigger than 10 nanometers. Then they should give you a stable signal.
Thanks for your talk. Like, I have a question about the cave monitoring. You say it's preliminary, but what's your idea about it? Do you think about like particular color inside the cave? Or?
Yeah, I think Samuel may be the guy for you to
Yeah.
talk. What I've been like struggling with Nicolas and Valdir is like adding at least watch glasses to understand like when it's being delivered and how much we need and what is the meaning of this. Also, what I've been looking for some works in Slovenia where they track like the CO2 variation in the soil. I would think that if we're thinking about like extracellular magnetite, we swamp this microbial activity, and then as we rise from these wet and dry cycles, that's when we start to have a lot of enrichment of the magnetic minerals. So combination of this like soil monitoring and cave delivered, it's been that's like when I think that it should give some better keys of the evolution. Also, there was a study in China where they took like a forest, and then some part of the cars there was no vegetation, and what they found out like only with I think 4 drips is that there is like more sediments coming from when there is no vegetation cover compared to, so there is like the rhizosphere like it's probably holding more of this delivery of the soil. So, but I think that's something that monitoring could start to give us more sense of how to interpret the magnetic mineralogy.
We have another question.
One quick question. You take your sample from the side, not from the main axis. So there's any correction or either measurement or calibration to deal it like the main section?
Yes, actually, because I take a slab, I can take one layer. Let me see if there's a good example. So imagine that I can track this layer from the front and from the back. So then when I position like each specimen that I take, I can calculate the true depth. So I calculate like, which is like very tectonic really. So you calculate like where is you can actually find the fold axis of the stalagmite. And then with this I can try to unfold when I unfold, you see that it's not actually a fold because the magnetic mirrors, they're already deposited in the limbs. So, but yeah, that's some kind of control that we're trying to figure out. Because a lot of why this is important. Rock magnetism, you think like you can take a lot of more samples if you go to the sides of your sample to have better statistics. But actually it's not true, because if you're seeing a lot of effects on the sides, probably it won't be good. It'll be good to keep the central part as part of this research. But I take a very careful, like when I'm cutting this, because it's the most valuable part, I would say, from the stalagmite. So it's I talk a lot to people before I do any harm to the samples. I get very intimate to the sample. Let's put it
You have to collect your own sample to play with that material.
Yeah. Sometimes, yeah. But usually, when I first started research, I came here and I looked for the archives, and that's when I start to dig and find like, oh, this cave could work and this one do not.
Thank you.
Could I add a quick one?
Yeah, of course.
How big is the sample that you cut? How much do you need?
I need a 1 centimeter, no, half centimeter high, 1 centimeter width, and that's good enough.
About a gram or something like that.
Yeah.
Yeah, go ahead.
Can I have a quick question? It was very exciting to see, but like I was wondering how do you differentiate between ex situ and in situ magnetic mineral? Like
In the goethite, we don't.
yeah, let's say you have a flooding and you have detrital material grains, existing grains. So how they influence your data? So they are from different time origin. So maybe they are older, not when Speleothem is growing. So how do we take care of this?
Yeah, that's a good question. I think that Samuel has been challenging this, like when it's floating and when it's drip water. We think that mainly when there is like a high concentration of magnetic minerals, it's more floating. And when there is like a, especially like this, all the samples they have these magnetic minerals, and we don't think there is some coercivity changes probably, especially that oxidation that's going on, but it's not very clear right now. I think that another thing that's when does the stalagmite grow should influence like this, because we are splashing and then there is like all the dripping and it's washing, and because you can have like a floating and then you start to wash this. Is this able to mobilize your magnetic minerals and then reorient itself? So that's a good question. I don't have an answer. I have more questions than answers. So.
Thank you.
We have time for one more question. Yeah, go ahead.
Yeah. So, you need, for Speleothem, it has so many dark layers. It's kind of hiatus between two layers. So how can you identify how long the hiatus?
I usually by visual inspection and I avoid the hiatus as much as I can. So that's an unfortunate part of my, especially that iron oxides, they are very marked by hiatuses. So that's I try to avoid and find a sample that I actually do not have. Or at least they will provide me an average signal that it's still in a good resolution.
All right, well, let's thank Plinio one more time for their And then I think now Marcella is going to come down and give some instructions about the lab tour.
Pode parar aqui no túnel laboratório. Tudo bem, valeu.
Okay, so